Alrighty, in the last video we went through and we proved two conditional statements and set up the proof that we were going to do to show that these four statements are equivalent. So what we're going to do now is just finish it up. I just wanted to give you a little bit of a breakdown here so it wasn't too much to digest at once. So hopefully you followed along and understand that we're trying to prove these four statements are equivalent, and by proving that these conditional statements are valid will allow us to conclude that these four statements are equivalent. So if you need a refresher on that, make sure you look back on the last video. But I'm going to go ahead and keep going. So we proved statement 1 and 2. Now we want to prove statement 3 and 4. So let's just go ahead, and like I always like to do, I like to just, before I dive into trying to write out complete sentences of these proofs, I like to make sure that I've got a good foundation going and I really understand how I'm going to go about proving this before I get started too far into my into writing out the actual proof. So this is my scratch work, so just follow along with my scratch work here, and then we'll put it into the proof that we're working on here. Alrighty, so we're trying to prove this conditional statement. Our hypothesis is that 3 times some integer plus 1 is odd, and our conclusion is 3n is even. So we're taking a fresh look on this statement, right? We're not using anything from the other two proofs. All we know about n is that it's an integer, okay? So with our assumption here, you could go about this a couple of different ways, right? A few different ways. We have a direct proof, we could do proof by contraposition, we could do proof by contradiction. And so, you just kind of got to pick a method, go with it, see where it gets you. And if it doesn't get you anywhere, then try another one, okay? But I'm going to try direct proof because that's usually my starting point. But one thing I did think when I first saw this was that I noticed that my conclusion, this expression in my conclusion is actually simpler than my expression in my hypothesis. So I thought maybe I would want to do a proof by contraposition so that I started off with 3n and built up to 3n plus 1. But I think it's going to be about the same amount of work when I thought about it a little bit more. So if that's something that sounds appealing to you, then you could totally just prove if 3n is odd, right? Because the contrapositive of a conditional statement is the negation of the conclusion implies the negation of a hypothesis. So if you wanted to prove this by contraposition, we'd prove for any integer n, if 3n is odd, then 3n plus 1 is even. Okay? Either way, we'll get there. We'll get there, okay? So what I'm going to do then is I'm just going to do direct proof because that's what makes sense to me right now, okay? This will work, right? Again, try it, email me if you have questions there. I'd be happy to walk you through more, okay? So let's think about a direct proof. So I'm going to assume my hypothesis. So assume hypothesis is true, and then prove that that means my conclusion has to be true, okay? So we're going to start by assuming that 3n plus 1 is odd, which means it's going to be 2 times some integer plus 1, okay? And just like we saw in the last one, right? Remember, we just subtracted 1 from both sides? We can definitely do that here, because remember, we're trying to conclude something about 3n, okay? So notice, check it out. We have our conclusion actually already, just a little bit of algebraic manipulation, and then also using the definition of that odd integer. So nothing too crazy there. Hopefully you can see that we've gotten to our desired conclusion that 3n is even. So let's just write this up to kind of wrap up what we've done here. So we're proving statement number 3, and our leading assumption was that 3n plus 1 was odd. So we're going to start by saying assume that 3n plus 1 is odd. Okay, then we're going to apply that definition just like we did in our sketch. Then 3n plus 1 is equal to 2 times k plus 1. Notice k is a local variable to this particular proof, okay? So it's okay to overlap with these other ones because now I'm starting all over without knowing anything about n. So this k is different, right? So it's okay. If it, if you'd rather use like m or l or, t or something, that's fine. But it's not a necessity. It's when you are working within one conditional proof and you start overlapping your variables, that's bad because you're making additional assumptions about how those different values are interacting, okay? So kind of note that because that's important. So if 3n plus 1 is odd, then 3n plus 1 is equal to 2 times some integer plus 1. And just make sure you declare your integer, your variables. So we're saying for some integer k. Okay. I'm just going to say equivalently, since just subtracting 1 from both sides, we still have a valid equation, still holds the same solutions, right? Okay. All right. So now we've shown that 3n is 2 times some integer. Thus, by definition of even integers, we know that 3n is even. Okay, now we're done with that proof of this conditional statement, this third conditional statement that if 3n plus 1 is odd, then 3n is even. Okay, so now we only have one left to do. Let's see if we can figure this out. We're trying to show that if 3n is even, then n is even. Okay, and this might be one where we could try, a little different method outside of a direct proof, but I think we can probably make a direct proof work here. Let's see what we've got. And once we get into the next module, so it'll be module 4, well, it'll be the number theory module, okay? We'll actually have an even nicer way to present this when we start talking about divisibility, okay, and prime numbers. So that's exciting, but for now, we're just kind of stuck with using the definition of even and odd integers and our basic properties of real numbers and integers involving multiplication, addition, subtraction, and those types of things. So we're a little bit more restricted at this point. So let's see. If we were doing a direct proof of this conditional statement, we'd start by assuming 3n is even and trying to conclude that n is even. I think I'm going to go with a proof by contraposition here because it's easier for me to go to n odd implies, right, because that's the negation of my conclusion here. The negation of n is even is n is odd. And the negation of my hypothesis is 3n is odd, okay? This is just like a more forward way of looking at it, right? Because to go from n to 3n, all I have to do is multiply by 3. Here, I have to divide by 3, and that gets a little bit funky, okay? So it's nicer to be able to multiply by 3, okay? Yeah, you'll see if you play around. Okay, so let's do a sketch and then let's dive into it because I think we pretty well have it down here. So if n is odd, then n is equal to 2 times, let's use L now, some integer plus 1, okay? L is an integer. Okay, then we're trying to figure out and conclude something about our conclusion here. So what's 3n? Well, we're going to multiply that new representation of our integer n by 3. That's going to give us 6L plus 3. Now, 6L. All right, now we want to show 3n is odd, okay? We want to write it in the form 2 times some integer plus 1, okay? It can be, it doesn't matter what integer, all that has to be satisfied is that this is an integer, okay? It could be an expression, but as long as that expression represents an integer, you're fine, okay? So what I'm going to do here, because I know I want this plus 1, I'm going to make it happen. I can always add 0 to an expression. So if I subtract 1 and add 1, I will get that 1 that I want. Oh, I was thinking 0, I wrote 0. Okay, because I'm really just adding 0 there, right? Because -1 plus 1 is 0. So I'm not changing anything crazy, okay? So I've got 6L plus 2 plus 1. All right, there's my plus 1 that I want. Does this give me the 2 times some integer? Let's see. Let's factor out a 2. 2L, or excuse me, if I factor out a 2 from both of these terms, 2 times 3L plus 1 plus 1. Okay? And we did it, right? We proved that 3n is odd because it's 2 times some integer plus 1. Okay? So let's write that up. And then we're done. So that was a lot better than 12 of these conditional statement proofs, right? So we really saved ourselves some time by thinking through and applying those rules in inference. Okay, so let's think about statement number 4. So our starting assumption, let's just make clear to our reader that we're using proof by contraposition here. So we actually are trying to prove the contrapositive of whatever is being proved in this little paragraph here. So I'm just going to start by saying, for proof by contraposition, assume, what was our assumption? Our assumption was that n is odd. I think it was n is odd. So let's just double check on our sketch here. Yeah, so we started with n is odd, and then we wanted to conclude that 3n is odd, okay? All right, assume n is odd, okay? Then, by definition of odd integers, n is equal to 2l plus 1 for some integer l. Okay, what else do we know? We're trying to conclude something about 3n, okay? Now, you might be saying, well, an odd integer times an odd integer is odd, okay? I totally agree. But if you're going to reference that in your proof, you need to be able to prove that statement, okay? So pretty much what we're doing here is, proving a specific case of that statement. So if you're going to use that, then I expect a little lemma, and I expect you to be able to prove that the product of an odd integer times an odd integer is odd, okay? So I hear where you're coming from, but you've got to support all of your statements that you're applying, okay? So let's see, note 3n, because we're trying to conclude something about 3n, so we are going to apply this new representation of n and substitute it in for n, and then we'll get 6l plus 3, and I'm just going to go ahead and let our reader fill in this work here, okay? All right. Thus, 3n is 2 times some integer 3l plus 1 plus 1. Hence, by definition of odd integers, n is odd. Okay, and we're done. We've proven those 4 conditional statements, and those 4 conditional statements, as we set up in the beginning, show that those 4 statements are equivalent.